All right, hi everybody. We are working on 9.4 notes, which are basically we're just going to keep talking about whether a series converges or diverges. And now we get to look at a slightly more complicated series. But before we do that, I just want to review some of the things we've talked about so far of how to determine if it converges or diverges. So like the first thing that I recommend you do is do the nth term test for divergence, which is that thing where you take the limit as n goes to infinity of a sub n, and if it doesn't equal 0, then it diverges. Right? It's just something you can do real quick to see if it diverges, because if it diverges, you're done. If it does equal 0, then you're not done. You have to actually show that it converges, because it could still diverge. Okay. The next thing we want to look for is is it geometric, right? Is it a geometric series? What's the geometric ones were the a times r to the n, and the rule there was if r was greater than 1, then it diverges. If r is between 0 and 1, greater than or equal to 1, then it converges to 1 over 1 minus r, right? So you can actually find the sum real easily that way. The next easiest way is the p series, which has the form 1 over n to the p. So example would be like 1 over n to the first, 1 over n to the second, so on and so forth. And the rule there is if p is greater than 1, it converges, and if p is less than 1, it diverges. There's no quick and easy formula to tell you what it converges to if it does converge. And then we get into like some of the more complicated things, such as the integral test, which there's these conditions that have to be met, right? It has to be, all the terms have to be positive, all the function must be continuous, and it must always be decreasing. So which requires you to take a derivative. It's kind of involved, very involved. And then this says if the integral, if the infinite integral, right, if the integral from 1 to infinity of f of n converges, then the series also converges, but it doesn't tell you what it converges to, right? Even if you find this number for the infinite integral, you're not going to be able to determine what it converges to. It won't be the same for this series. And then the last thing, which was actually one of the first thing we did, what is quite very conceptually difficult, is the partial sums, right? You find S1, S2, S3, and then you find a sequence of what these numbers equal, and you take the limit. You take the limit as n goes to infinity of S sub n, right? You find the rule for the partial sums, and you find the limit, and this one will actually tell you what it converges to, right? Which again, that one's very involved. So let's look at some examples. Think of our thought process here. Number 1, you're looking at this and you may not recognize it as anything special right now, but the first thing you should do, even if you don't write it down, you can do this in your head. What's the nth term test, right, for divergence? Take the limit as n goes infinity. You're going to get 1 over infinity, which goes to 0. So that test for divergence didn't tell me anything. Right, so then I want to look at it. Well, is it geometric, p series? Is it neither? Can I do the integration thing? We've done one similar to this. We can rewrite 1 over 2 to the n as 1/2 to the n power, in which case it's geometric. And r is 1/2. And since r is less than 1, the series converges to 1 over 1 minus 1/2, which is 2. Right? We like geometric series. They're very easy. The next one is this, which again, the first thing we're going to do is just that nth term test for divergence, because if this works, then we're done. 1 over infinity, which is 0. So again, If I would have gotten 1, I could have said it diverges, right? If I would have gotten 1/2, I could have said it diverges. But because I get 0, I can't say it diverges. It doesn't mean it absolutely converges either. But so what we need to do is look at it and say, well, it's not geometric, right? Geometric, you have a constant to a variable power, right? This one, you have a variable to a constant power, right? So that's different. So variable to a constant power is actually the p series here, right? This is 1 over n to the p. This is p series, where p equals 3, right? So since p is greater than 1, this series converges. If you wanted to show what it converges to, like at this point, you'd have to do the the partial sums and find the limit of the nth partial sum, which we're not going to do right now, as that's not the point of this one. Next one. Again, we want to just quickly check. Let me erase some of this over here, but we want to quickly check the nth term just to make sure, right? So we're going to do the limit n goes to infinity, make sure it doesn't just diverge, and we can just be done. And again, this is the bottom's going to be growing faster, right? So it's going to be small over big, which eventually goes to 0. You could do L'Hopital on it or something too if you want, and I should be saying goes to 0, not equals 0. So again, that test for divergence didn't tell me anything. So it's clearly not geometric, right? It's clearly not p series because there's like an n on top and it's kind of messy on the bottom. So at this point, the only other thing we know is the integral test, which is basically we're going to define a function with the same term as this. Sorry, this should have a sum on it, right? It should go from 1 to infinity. We're going to define a function the same as that. The difference between the function and the series is the function is continuous, like it's all the connected points, whereas the series thing is like discrete points like this, right? So that's like the main difference between a function and a series. And what we need to show for the function is that it meets the 3 conditions: that all the terms are positive, that it's continuous, and it's decreasing. And that's for x values greater than 1, or n values greater than 1. So like if I'm plugging in numbers greater than 1 here, those are always going to be positive. And if I'm plugging in n values greater than 1 down here, those are always going to be positive, right? Just if you think about it, there's no way to get a negative out of that. There's no negatives in there. So that condition 1, that it is positive, all the terms will always be positive, right? So that's good. 2, is it continuous? Well, you want to look at the denominator and say, is there anything that can make that 0? And so basically you're asking, is there any way to make n squared plus 3 equal to 0? No, it will never be 0. So yes, it's continuous. And 3 is like the kind of the harder one to do. You have to show that it is always decreasing, right? So the way you do that is you take the derivative, and show that it's always decreasing. So the derivative here is going to be 1 times n squared plus 3 squared minus 2 n squared plus 3 to the first times 2n times n all over n squared plus 3 to the fourth, right? If I square a square, you get to the 4th power. And let's clean this up. Cleaning this up, you can show that it will equal, that we can go and expand this first thing here. You're going to get n to the 4th plus 6n squared plus 9. Simplify all this stuff, right? This is 2n squared. And then you distribute this negative 2 in there, and you're going to get negative 4n to the 4th minus 12n squared. And it's all still over n squared plus 3 to the 4th. And so a little bit more cleanup, combine, sorry, this is to the 4th power here, because we have n squared times n squared. So clean this up a little bit more. You get a negative 3n to the 4th minus 6n squared plus 9 all over n squared plus 3 to the 4th. And a little bit more, if you factor this, you get negative 3 n squared you can see how this integral test kind of a pain in the butt, because we got a lot of work just to show that it's decreasing. N squared, negative 3n squared, this one's going to be plus 3, and this one's going to be minus 1. And we're trying to show that it's always decreasing after, for n values greater than 1. So what we can show is this is always, the bottom's always positive, so I don't have to worry about that. And then the top I have to show, if I plug in numbers bigger than 1, I get negative values, right? So just like plug in 1, if you plug in 1 you get 0, right? Plug in 2, you can imagine this is positive. Plug in 2, this is also positive times a negative, right? And then for any n value greater than 1, you're never going to get a negative value here, right? So like neither of these two for n values greater than 1 will ever give you a negative, right? Like, because the only way to get a negative would be if the n squared here was less than that negative 1. So what this shows is this, for n greater than 1, this is always negative. So we have a negative derivative, right? So what that shows is the derivative is less than 0, it's negative, which means that third condition is met, it's always decreasing, right? We just have, like, again, all we've shown so far is that this test can work. Now that we know it can work, we actually need to integrate, right? So now it says, well, if I can find what the test says is, okay, now that I know it can work, I'm actually going to take the integral like this, which we usually just set up a limit from, let's just say a is going to infinity, 1 to a of respect to n. This is a u sub problem, right? You say, oh, well, u is n squared plus 1, therefore u squared, therefore du is 2n dn, and dn is du over 2n, right? And you come over here and you plug that in, so we have the limit as n goes to infinity of 1 to a n over u squared, and then that dn becomes du, oh, I just meant to change colors. Oh yeah, I did. Du over 2n. These guys cancel, right? And then you can integrate. This turns into, I'm just going to leave the limit out for just a second. So integrating gives us 1/2 u to the negative 3 over negative 3, which gives us negative 1/6 u to the third evaluated from 1 to a, and you just plug those in. Oh, and then we plug u back in, and we're getting the limit as n goes to infinity of negative 1/6. Let's just write it this way. A goes to infinity, not n. N squared plus 1 to the third, and we're going from 1 to a, so we plug in 1, we plug in a, and we get, and we plug in 1, and we get minus negative, which is going to turn into positive 1/6 1 squared plus 1 to the third, and we're taking the limit as a goes to infinity, and we're almost done. As a goes to infinity, this whole thing is going to go to 0, right? Because a is on the bottom, you're going to get 1 over infinity, and then this is just a constant, so this one goes to 1/6 times 1 plus 1, 2 cubed, so 1 over 6 times 8, 1 over 48. So it converges. right? The integral converges, therefore the series also converges, but the series does not converge to 1 over 48. It converges to some other number, right? So that integral test is pretty involved, and it's pretty disgusting. Okay, so let's go on to the new stuff that we're trying to learn, which is a direct comparison test. What this is doing is we're going to compare a more complicated series to something that's a little simpler. And the idea is so first of all, notice that everything's greater than 0 here. And if the terms in this series, AN, are less than the terms in BN, right? Meaning like A1 is less than B1 and A2 is less than B2 and A3 is less than B3, so on and so forth. Then, if the bigger series, BN, converges, then the smaller series also converges, right? So if I can show that this series that I know is bigger than this other one converges, then the smaller one also converges. And if I can show that the smaller one diverges, then that will show me that the bigger one also diverges. All right, so it's really kind of weird at first, but let's see how this goes. Okay, so here we are. We're looking at A here, which we're wondering what this series is, if this converges or diverges. And what we want to kind of recognize is that this resembles the series, right? It resembles the series resembles this series, 1 over 3dn. The only difference is there's like a plus 2 down there on the bottom, right? And this series is what, right? It looks very much like the example we did above. It looks like a geometric series, right? 1/3 the n. So this series here converges, right? Because it's a geometric series, and r is less than 1. So what we need to show, right? We know that this one converges. What we need to show is that the one that's in question, this one here, all the terms are less than the terms in this one, right? So we need to show that the terms in this one are always less than the terms in this one. So we can kind of do this. Let's do this first one piece by piece, right? So let's just do. Let's call this AN, and we'll call this BN, right? So A1. Plug in 1, you get 1 over 2 plus 3, right? 1 over 2 plus 3 is 1 over 5. A2, plug in 2, you get 1 over 2 plus 9, which is 1 over 11. A3 is 1 over 2 plus 27, which is 1 over 2 plus 27 is 29. Okay, and so there's the first few. We could do the other ones as well. So let's do B now, and let's see how that works. If I plug in numbers to B, then it's 1 over 3 to the first power, which is 1/3. And then B2 is 1 over 3 squared, which is 1 over 9. And A4 is 1 over 27. And so you're asking, well, which one of these are greater? Well, we added 2 to the, you can kind of see it when you do it. We added 2 to the denominator every single time, and that's the difference between the two, is that 2 in the bottom. So we're dividing by a bigger number, which makes the terms in AN, these terms are actually smaller, right? Because you're dividing by a bigger number. And that will always be true for all the terms, right? Because you're always adding 2 to the same thing you would have here. So you're always going to be dividing by a smaller number. So what we can show is set up this equality here that AN, we already know this, is 2 plus 3 to the n, which is less than 1 over 3 to the n, right? And 3 to the n was that BN series. And so because, A to the n is less than B to the n, right? This is that first case. A to the n is less than the B to the n. And B to the n converges, right? The bigger one converges, then the smaller one must also converges, right? So we'd say, by the direct comparison test, you know, the series converges, right? Again, it's not going to tell us what it converges to, but it tells us that it does converge. All right, so that's that one. Let's look at the next one, which is 2 plus radical n. It looks very similar to the series 1 over square root of n, which, right, looks very similar to 1 over square root of n, which is the same as 1 over n to the 1/2, which is a p series, right? That's a p series with p equal to p series p equal to 1/2. So you ask yourself, well, does this one converge? No, this one diverges, right? P is less than 1, so it diverges, which means what we need to show is that this one, right? So if an diverges, if the smaller one diverges, then the bigger one diverges. So what we need to show is that this one is smaller, and then we can show that that one diverges. So let's think about it. This is like very similar to the other one, right? If I'm adding 2 to the denominator, that means this one's actually going to be smaller, right? Because you're dividing by a bigger number. So we can't compare this, right? What we would say is that for n greater than or equal to 1, right? So this is not what we want, right? We're showing an and bn. And what we know is that bn diverges, but that won't tell us that an diverges, because in order for this to work, it would have to be bn that is smaller. The smaller series would have to diverge. So this doesn't actually work, right? So instead, we can choose a different p series. Let's try the harmonic series, 1 over n, right, which also diverges, right? 1 over n diverges. Can we show that 1 over n will always be smaller than 1 over 2 plus square root of n, right? So let's try it. Let's do this one first. The terms are, plug in 1, you get 1 over 2 plus square root of 1 is 3, 1/3. Plug in 2, so this is n equal 1. Plug in 2, you get 1 over 2 plus square root of 2, which, you know, we'd have to use a calculator to figure what that is. And the next one, plug in 3, you get 1 over 2 plus square root of 3. And then we can do 4, 1 over 2 plus 2, which is 1 over 4. Okay, and let's try the terms for 1 over n. 1 over n would be 1 over 1, 1 over 2, 1 over 3, 1 over 4, which can we verify that these are actually bigger, right? We want to show, we want to show that these are smaller. Sorry, one second, let me pause this to make sure I'm doing this right. Okay, yeah, this is right. But so far what you should notice is that this one's actually smaller, right? This top one here is actually smaller because you're dividing by a bigger number. But let's keep going, right? Let's just keep looking at this. So this next one's going to be 2 plus square root of 5, and this one's going to be 1/5. This one's going to be 2 plus square root of 6, and this one's going to be 1/6. And then look after 4, right? They were equal at 4. After 4, what's happening? After 4, you get 1 over 2 plus square root of 5, which that is 2 plus square root of 5 is 4.3, right? So here, this is 1 over 4.23, which, since we're dividing by a smaller number, is actually bigger, right? So after the fourth term, this is bigger and this is smaller, right? And so what we can show is that the smaller series diverges, right? So in this case, since the smaller series, 1 over n, this one is less than 1 over 2 plus square root of n. Now let's add a condition here. This is for when n is greater than or equal to 4. Since 1 over n is less than this, and 1 over n diverges, and the series diverges, 1 over the series 1 over 2 plus square root of n also diverges. Right? So, you know, that one took a little bit of working with, but so you can see that how that might come up sometimes. Okay, so let's look at that last one if we have space. Okay, so here's this last one. We want to find a similar series to this one. So similar to this one is, it kind of looks like just 1 over n squared, right? Which 1 over n squared is a p series, which converges because p equals 2 and p is greater than 1, so it converges, right? So what we need to show is that if this one's going to converge, then this one needs to be the smaller one, and this one needs to be the bigger one, right? So we need to show that like all these terms are smaller than that term, right? And you can reason through this because remember, again, if I do 1 over n squared, that's going to be bigger than 1 over 3 times n squared plus 2, because in this case you're dividing by a bigger number, right? So if you're dividing by a bigger number, you're going to get a smaller. So we can show that in this case 1 over 3n squared plus 2, those terms are always less than or equal to 1 over n squared for n greater than or equal to 1. So by the direct comparison test, because 1 over n squared converges and this one's smaller than it, this one also converges, right? So the series converges. All right, so again, you're just trying to find something that it's similar to, show that it's either smaller or bigger, and then you can say that it converges. All right, so here's yet another test that we're going to do. Actually, before we do that, I wanted to come back up here and just write these two things in a little bit, like, you know, simpler words here. So number one is saying that if the larger series converges, then the smaller also converges. Right, that's what this first one says. And the second one says if the smaller series diverges, then the bigger or larger also diverges. Right, so that's what those are saying in, like, you know, normal person language, and not, you know, that crazy symbology there. All right, so next is the limit comparison test. We're going to take a limit and compare two things. So again, there's some conditions that must be met. All the terms must be positive for both series. Then what it says is if the limit as n goes to infinity of an divided by bn exists, right? This is what they're saying, it exists, it equals some number, it's not infinity or negative infinity or whatever. If it exists, then either both series converge or both diverge. So what we're trying to do is one of them is going to be the one that's given to us, and then we're going to find the other one that is similar and divide by it, and then take the limit. And if the limit exists, then we can use one of them. We can use the one that we know the limit of, or sorry, we can use the one that we know either converges or diverges to show that the other one converges or diverges as well. All right, so that's a mouthful. Let's just try this, right? So let's look at this one, number one, and let's think about, well, what's a similar series, right? So a similar series is n equals 1 to infinity of 1 over n. Right? If you just eliminate the a and the b, you get 1 over n, which is a divergent p-series. It's the harmonic series which is divergent, right? Divergent p-series. So what we're going to do is you could call this like an, and you could call this like bn. This one could be bn. So we're going to do the limit as n goes to infinity of 1 over a n plus b divided by 1 over n, right? And then let's clean this up. The limit as n goes to infinity of, instead of dividing by 1 over n, we're going to multiply by n over 1, and we get n over an plus b, which we're going to use an n behavior model, right? Those two will grow at the same rate, so this is going to go to 1 over a, right? So the limit exists. What this shows us is the limit exists. It is a finite number, and so since 1 over n diverges, the series 1 over n diverges by the limit comparison test, so does so by, let's do LCT, the series, this series also diverges. All right, let's do another one. Again, let's just call this an. We want to find some other bn that's similar to that. Again, it's probably just like, you know, the series 1 over square root of n. And 1 over square root of n is a p-series with p equal to 1/2, right? It's n to the 1/2 power, which this diverges. All right, and so we're going to do the limit as n goes to infinity of an, which is this, divided by this. And simplifying again gives us square root of n over square root of 3n minus 2. And again, like this 2 becomes insignificant. All that we're left with is square root of n over square root of 3n, which converges to square root 1 over square root of 3. So it exists, right? The limit exists, which means that since we know that bn diverges, this one must also diverge, right? So the series diverges. Okay, next one. 1 over 3n squared minus 4n plus 5. A similar series for this, just maybe 1 over n squared. Right, so we're going to take the limit, again, maybe this is an and this is bn. We're going to take the limit as n goes to infinity of an divided by bn. And you can see this process so far is very repetitive. We've done this a lot. This is going to be n squared on top, 3n squared minus 4n plus 5 on bottom. And it's an infinite limit, which means we can use the n behavior model. Just look at those. So this converges to 1/3, which means that the direct comparison test works. We should have talked about this before, I guess, but does 1 over n squared converge or diverge? It converges, right? It's a p-series. P equals 2, which is greater than 1. So since this one converges and the limit comparison test worked, right? We got an answer. It's not, the limit exists. That means that our series, this guy, also converges. To what? We don't know, right? Like that's a different question for a different day. We don't know what it converges to yet, but we know it converges. All right, next one looks like this. N squared minus 10 over 4n to the 5th plus n to the 3rd. You know, finding a similar series can look kind of confusing at first, but basically you just want to look at something that, you know, is a simpler version, right? Just look at like the highest exponents maybe, and then like the terms in each one have the highest exponents, which looks like that, right? N squared over n to the 5th, which is basically just 1 over n to the 3rd, which again is a p-series with p equal to 3, which converges, right? So now we're going to do our we're going to do our limit comparison test, which is limit as n goes to infinity of n squared minus 10 over 4n to the 5th plus 3 plus n to the 3rd divided by, let's go ahead and use this one, I think it's going to be easier, n squared n to the 5th, which is going to give us n to the 5th times n squared minus 10 over n squared times 4n to the 5th plus n to the 3rd, and we're still taking the limit as n goes to infinity. And again, all that's going to matter, we can go ahead and do these, simplify them. Right, and again, we're going to use an n behavior model. Looking at those two, sorry, I wrote the wrong number there. N to the 5th times n squared is n to the 7th. Looking at your highest degrees, this converges to 1/6, and since it converges, or since the limit exists, then either both converge or both diverge, and since this one converges, this one also converges, right? So here we can say that it converges, right? That series we're given converges. All right, here's a couple more examples. Determine the convergence or divergence. So this one looks really similar to maybe square root of n over n squared, right? Just get rid of that 1. Which square root of n over n squared is the same as n to the 1/2 over n squared, which is the same as, take 2 minus 1/2, right? Bring this 1/2 to the bottom. I guess I can write that step. N squared times n to the negative 1/2, which is going to be 1 over n to the 3/2. Right, and so this one is a p series with p equals 3/2, which means it converges, right? P is greater than 1. So we're going to do our limit comparison test. Limit as n goes to infinity of this one. So what we need to show is, that since this one converges, if this limit exists, then this other one will converge as well, right? So that divided by our other one, square root of n over n squared, which is going to equal square root of n times n squared over square root of n times n squared plus 1. These guys are going to cancel. And then the limit as n goes to infinity, those, those also, like this one becomes insignificant. We're looking at the highest degree here, which is n squared over n squared. So this goes to 1, which means the limit exists. And both series either converge or diverge. Since this one converges, this one also converges. All right. Next one. Let's find a similar series. Again, we just want to make something that's very similar, but like this. And right, so we're just kind of like simplifying. Actually, that's not quite right. It'd be like this, right? You need that n up there, which is the same as 2 to the n over n squared. So we want to know, does this converge or diverge? Like first, like the simpler series, does it converge or diverge? Well, you can just do, it's not geometric, it's not a p series because it has this, it's maybe like a mix of geometric and p series, but let's just do the nth term test for divergence, right? What's the limit as n goes to infinity of 2 to the n over n squared? Well, that actually goes to infinity, which is not 0, which means this one here diverges. Right? So since this one diverges, we need to show that if this limit here exists, if this limit exists, then this series also diverges. All right, so let's clean this up. N to the third is going to be on top, so it's going to be n to the third times n 2 to the n over n 2 to the n times 4n to the third plus 1. Let's do some cancellations. This can cancel that, and this can cancel that, and so we're left with limit as n goes to infinity of n to the third over 4n to the third plus 1. We can use an n behavior model and just say, well, everything else is going to be insignificant except for those two. So it's basically the same as limit as n goes to infinity of 1 over 4, which is 1/4. Since the limit exists and this series diverges, so does this one, right? So the series also diverges. Got it? There would be cases when this would, like, this thing might fail, right? If you were doing this limit and you got infinity, then this limit test would fail, and you would have to figure out some other way to do it. All right. I hope this is helpful and not too long. The problems you need to work on are here. I've printed them out and put them in a notebook.